Hello everyone, my name is Mouayed Bellah Nafeh and I'm a PhD student in IUSS Pavia in Italy. I'd like to welcome you all to my presentation on the Simplified Seismic Assessment of Infilled RC frame structures, which was co-authored by Gerard O'Reilly and Ricardo Montero from the Rose Research Center. We will kick things off with the motivation behind the study, followed by an overview of the assessment of infilled RC frames using equivalent single degree of freedom oscillators. Then, empirical relationships derived using extensive nonlinear dynamic analysis and equivalent SDOF systems are presented. Subsequently, the validation of the developed relationships is performed in terms of the predicted intensities corresponding to arbitrary performance limits and the associated uncertainties. This is done in comparison to the same metrics obtained using a hazard-consistent nonlinear dynamic analysis using multiple stripe analysis. Italian and European reinforced concrete frame buildings with masonry infill panels comprise a significant portion of the Mediterranean building stock. Before the 1980s, or before the introduction of suitable seismic provisions, buildings in Italy in specific and also across southern Europe were generally designed and constructed to resist gravity loads only. This made them increasingly vulnerable to high levels of ground shaking, where high levels of damage were observed in past earthquakes. Structural elements designed this way were typically characterized with inadequate seismic detailing. For example, the use of smooth rebars, low compressive strength for concrete, and no consideration for a ductile failure mechanism. Unreinforced clay brick masonry infills were typically used as partitioning and facade elements, based on their thermal and acoustic insulation, fire retarding, and moisture control behavior. These elements, however, were not considered in the structural design, and therefore their effects on the structural response were neglected. Several experimental and analytical studies have outlined the detrimental effect of masonry infills on the global lateral response of the structural system, characterized by a significant addition in lateral stiffness, followed by a sudden loss of lateral strength capacity due to localization of damage on one or several stories. The assessment of the seismic performance of structure requires accurate quantification of the exceedance of any structural demand-based performance level. The latter is typically quantified using fragility curves, which link the probability of exceeding predefined thresholds of demand for a given intensity level of ground shaking. These are usually the end result of extensive numerical analyses. To reduce the computational effort and time required by such analysis, simplified tools and methodologies for the assessment of RC frame structures have emerged, such as SPO2-IRA. These simplified approaches utilize RMUT relationships for a direct estimation of the seismic demand and capacity. The aim of these tools is to supply users with aid in the quantification and mitigation of seismic risk compatible with different guidelines such as FEMA P58. The advantage behind SPO2-IRA and other similar tools is that it offers the ability to relate the force deformation capacity of a frame structure to its dynamic counterpart through IDA curves. This is done by performing a static pushover analysis of a building and fitting a multilinear backbone. The results of eigenvalue analysis are used to transform the multi-degree of freedom system to an SDOF via the transformation factor gamma. Then, the strength ratio and ductility are being interpolated for the 16th, 50th, and 84th percentile. The tool developed herein aims at filling the gaps due to behavior incompatibility due to the addition of infills. As we can see, the tool itself, SPO2-IRA, was developed for bare RC frames and moment fracturing and connection fracturing moment resisting frames. This, when combined with the static pushover curves of an infilled RC frame, results in an underestimation of the median capacity, such as the median collapse capacity from SPO2-IRA and from the actual analysis. As such, empirical relationships are developed to extend and implement the response of infilled RC frames. Moving on to the assessment of infilled RC frames and equivalent SDOF oscillators. For the assessment of infilled RC structures with equivalent SDOF system, 10 case study buildings representing infilled RC frames with various infill strength are selected and modeled in OpenSees. A static pushover analysis is then performed, followed by an eigenvalue analysis to obtain equivalent SDOF properties and subsequently revert the MDOF to an SDOF system. Having done so, the comparison is performed using two existing modeling approaches from the literature and a novel proposed approach for modeling equivalent SDOF systems of infilled RC frames. Incremental dynamic analysis is then performed, and the trends in the IDA curves are compared. 2, 3, 4, 6, and 9-story weak and strong single-leaf infilled frames are selected. As such, a representative sample of frames with different heights and periods is selected. A static pushover analysis is then performed, and the addition of infills is observed when comparing the lateral response capacity to simple bare frames. Two different approaches from the literature are adopted to capture the overall performance of infilled RC frame through SDOF oscillators. Nonetheless, particular aspects may still require improvements to better characterize the lateral response. For instance, considering a defined ultimate displacement capacity of these structures is of undoubted importance when examining their behavior up to collapse. To this end, approach 1 may be more beneficial since approach 2 does not consider a defined threshold for ductility capacity of the underlying RC frame. On the other hand, what is favorable about approach 2 is the manner in which it segregates the masonry infill contribution from the RC frame contribution. Yet, this approach demands further attention since the subsequent response of the structure following the collapse of the masonry infill at the critical story in the building does not exactly become the response of a completely bare frame. Considering the above remarks, a more refined equivalent SDOF modeling approach for infilled frame is proposed and summarized herein, where the actual response of the infilled RC frame is combined with the structural response. Once the critical story has formed a mechanism and its infill panels have collapsed, the proposed model comprises a combination of this latter model and the infill contribution to give the 0, 1, 2, 3, 4 response initially, but reduces to the 0, 5, 6, 7 response once the infill has collapsed. A series of IDAs were performed to evaluate the suitability of the aforementioned equivalent SDOF models for dynamic analysis. The dynamic behavior of these models is compared to the response of the actual MDOF models. An example corresponding to a 2- and 4-story infilled RC frame structures is illustrated. The FEMA P695 far-field ground motion set was used, and the spectral acceleration on the fundamental period of vibration, SAT1, was selected as the intensity measure. IDA was conducted until the complete collapse of the structures, defined as reaching a 10% story drift in any story for a given record. The median IDA trace was computed from the individual ground motion at each intensity and the associated dispersions. The differences between approaches 1 and 2 and the proposed model are examined and compared to the response of the actual MDOF model. The strength ratio R, defined as the ratio between the recorded and yield spectral accelerations, is plotted against the ductility of the frames mu. For a given intensity, approach 1 appears to overestimate the dynamic response of the structure due to the model's oversimplification of the initial portion of the backbone curve. The use of a single peak point followed by a sudden drop in lateral load-bearing strength to model the effects of masonry infill tends to result in an increased flexibility and subsequently larger displacement demand when compared to the actual model. Maintaining the resistance with increasing levels of intensity is due to the adoption of a bilinear backbone RC frame response with no definition of an ultimate ductility threshold. Therefore, the SDOF oscillator is able to endure increased values of intensity without their IDA curves ever actually flatlining. In the absence of a proper failure point definition. On the other hand, for the SDOF model proposed, the median values are much more aligned with the median response of the actual model, especially the intensity at the collapse of the structures, demonstrating its suitability. As such, given the significant differences observed in collapse intensity estimation among the approaches examined, it is believed that the numerical modeling approach suggested here for infilled RC frames should be the one adopted in studies of this sort. With regards to developing empirical relationships for simplified assessment of infilled RC frames, a dataset of SDOF oscillators by adopting the proposed SDOF modeling approach with varying backbone parameters is developed through correlation-controlled Latin hypercube sampling representative of infilled RC frames. CLHS is used to reduce unintentional correlations between the different random variables. This is followed by incremental dynamic analysis on the SDOF dataset using the FEMA P695 far-field record set and subsequently processing the IDA fractals corresponding to the 16th, median, and 84th percentile. Then, the predefined backbone curve parameters, base shear against roof displacement, are normalized to obtain RMU, and the intensity measured engineering demand parameter response obtained from IDAs are also normalized to go from the SAT1 and delta to RMU. Final step includes conducting two-step regression analysis of each response branch. This is done primarily by associating the IAM-EDP relationship to a suitable regression function RMU, and then associating the parameters of the previously regressed function to the fundamental period. This is done for all the response branches, from hardening branch, softening branch, residual plateau branch, and the strength degradation branch. The end result is the empirical relationships implemented within an Excel spreadsheet. The spreadsheet tool can be downloaded from the following link. As per the case study validation, the building chosen to further validate the results obtained using the extended SPO2 IRA is a 3-story RC school building with masonry infills located in central Italy. The school building considered for the validation herein was constructed in the 1960s before the introduction of seismic design provision. A static pushover analysis is performed in both principal direction, and the multilinearization of SPO curves is performed. A model analysis is conducted. This is done to extract the first model shape corresponding to both principal directions and to compute the equivalent SDOF parameter. Having done so, the static pushover analysis and the model analysis results are then used as input for the tool. A hazard consistent multiple stripe analysis is also performed to process the fragility functions corresponding to selected limit states. The median capacity and dispersions associated with the chosen performance limits from the tool are then selected. A good agreement is observed between the estimated and actual fragility function parameters, as we can see from the fragility functions presented here. And to conclude, existing approaches to characterize the response of infilled RC frames via equivalent SDOFs are not entirely representative when compared to the response of detailed numerical models. A new backbone definition was proposed for the numerical modeling of representative infilled RC frames using equivalent SDOF oscillators. Empirical relationships are developed which incorporate the behavior of infilled RC frames based on extensive nonlinear time history analysis and statistical analysis. The applicability of the tool relating the static pushover curve of a structure to its IDA fractals was reviewed and seemed not to be applicable to RC frames with masonry infills. Hence, an extended SPO2 IRA tool in the form of a user-friendly Excel spreadsheet and a MATLAB script was subsequently developed, with the responsive infilled RC frames characterized by simplified backbone fit characteristics of their behavior was utilized. A new version of the tool has been published on the following link, which incorporates the average spectral acceleration as a suitable intensity measure. For further information regarding the updated tool, please refer to the following reference. Thank you very much for your virtual attendance, and for any further information you may require, please feel free to contact me. Thank you.